Welcome back, everyone. For the final lecture, we have Sergei who will give us his last course. Yeah, so in this lecture, I'll decode this mysterious title. So I'll move into explain it, although I mentioned integral bits yesterday, so they'll come up again, and I'll work on it. So what we did so far, we introduced for all kinds of manifold, and again, if you don't like three manifold, we think about just graphs. There's two series invariants, so they depend on input, the variable q, which is generic, and all of this additional decoration p, which again, if you like them, think about them. If you don't like them, there are plenty of examples here which don't require that. And what we know so far is that it has the form of q to some delta, and then two series with integer powered integer coefficient. So this delta is just in general fractional, but it has the form C0 plus 1 times q plus 2 to the squared, dot, dot, dot. So delta. And if you have this degree, this freedom to have parameter b, then everything actually depends on the general form already is something that those of you who have experience with CFT or vertex algebra can anticipate that it looks like a character, and that was indeed a theorem slash conjecture. In general, that's a horrible thing to say, but hopefully you know what I mean. It's a theorem for very simple graphs and conjecture for general graphs, in fact, general manifolds, that this object is a character of some logarithmic vertex algebra. Which I abbreviate as VOA, or the whole thing would be VOA. And again, this is a hot, popular topic on its own right in quantum algebra. So you can view this machinery as a factory for such inspiration and facts about logarithmic vertex algebras. So what is a character in general? So again, if you haven't seen this before, I can easily explain what it is. It's not something super complicated. Basically, vertex algebra is huge, infinite dimensional algebra. It's big, and its representations are also huge. So in practice, we all strive for this abstraction, and when we write papers, we try to be fancy and precise and abstract. But in practice, just a couple of weeks ago, actually, I was giving a lecture at the same place where Terry Gannon was giving lecture course on logarithmic VOAs. And he confessed to the audience, and I think that's a very good confession, that 99% of the time, we actually want to be as explicit and concrete. So our head should be up in the skies, but our feet should be on the ground. And most of the time, we actually want to work with very concrete things. So characters provide this very concrete way of encoding information by rather complicated representations of these rather complicated algebras. So if you have a representation, let's call it V. The natural thing to do is to basically take the trace over everything in V of q to the L naught. So this L naught in vertex algebra or conformal theory is called conformal vector. That's a special operator. And it basically gives grading to this infinite dimensional space V. The cool thing is that graded pieces are usually finite dimensional. In fact, we try to work with those which are finite dimensional. So basically, this is sum of graded dimensions here. So I mentioned elliptic genus yesterday, and similarly here, I can write either super trace, because we usually work in some kind of setting which could be either derived or have some other origin. where it's natural to view things as a complex or introduce minus signs. So this is actually either super trace, so that's one way to write it, or equivalently, I can write same thing, trace over representation of this vertex algebra, Q to the L naught, but then I have to say -1 to some another grading, homological like grading I. Okay. So that's basically what these characters are. In our context, this supply of modules is labeled by B, and actually refinement of this conjecture is that the choice of module of representation does depend on B, but for the same three-manifold, algebra is always the same. So they're modules for the same algebra. So in other words, choice of manifold mysteriously provides you logarithmic vertex algebra. So this is something we can, again, dive in and discuss a little more, but I want to kind of illustrate that this is not very complicated. And actually, this is good perspective to think about spectrum, not in the sense of homotopy theory, but spectrum of operator like Laplacian, or think about the shape of the drum that you can try to reconstruct from spectrum. In any kind of system, be it physical theory or mathematical problem. So suppose you have a very simple spectrum so that there is one dimensional space per one value of this grading. So this will be, I'll not think about this as some kind of energy. Okay, that's actually a good way of thinking about it. It's not exaggeration. It's not me trying to dumb things down. That's actually what happens. So suppose we have a spectrum where you have this sort of energy levels, N of the form m plus 1, okay, for instance, just as an example. Then explaining this sounds like a kind of complicated problem. It maybe starts resonating as quantum mechanical something, but I can encode this whole picture in one simple formula in the form of Q series. So basically, I'm going to write the same thing. My super trace of Q to the L naught, in this case, its energy, is going to be Q to the 1/2 because that's the ground state energy. I'm assuming that N is non-negative. And then I'll have 1 plus Q squared plus ... So it's exactly in the same form as everything we had before. So, and that's not a surprise. So every system, be it a system relevant to elliptic genus or this more interesting things that we're discussing, is basically packaging spectrum of some interesting system. And actually, physicist Sidney Coleman has this famous quote that life of theoretical physicists is a study of harmonic oscillator in ever-increasing levels of details. So, and that's true. So that's what physicists do. They study harmonic oscillator, then many harmonic oscillators. That's what we call quantum field theory, and then many complicated interacting ones. But you see that, yes, this formula, the simple geometric series, changes into some more complicated series, but the structure remains the same. This is ground state energy, and this is basically counting of levels with signs as they go up, and that's really what elliptic genus is. So if you didn't know this, it's not rocket science. That's what it is. Yeah.
And there's no alternating sign in the
second version. Oh, in this version, no, because I'm assuming this is just example. So as an example, take a simple system which has this ground state with energy 1/2 and only one state per next level. So it has a name.
Is the class of manifolds that are bounded below in like these eigenvalues like distinguished amongst? Like I guess I'm wondering, like, do you know a priori when your invariant will have some boundedness in the direction?
Boundedness in terms of that it will have this form that.
Without like, so the coefficients are just like integers, and like a priori they could be like going off to infinity in either direction.
Yeah, so a priori, at least originally, again, many years ago from physics, it was expected that that's true for all manifolds. all including those which we didn't talk about, and hopefully we'll touch upon later in this lecture. And by now it's been basically established mathematically that that's true. So yeah, for in our context, for all of them, that should be the form. And yeah, usually that's what one requires, but we don't want a Q to go in negative directions, and usually physics guarantees it for its own reason. Mathematically, this comes from usually in one way or the other. For example, elliptic genus in pretty much all cases has this property, this 2D, 3D combined elliptic genus, which is what this is, what we're discussing, also has these properties for its own reasons and so on. So, in other words, it never goes back in negative direction. So this has sort of several implications, or again, this is simple principle, but it's very powerful, and there are lots of things you can basically, if you embrace it, that this is a way of encoding the spectrum. There is a lot you can actually start trying to learn from. One thing that I mentioned to you before, that we care about this 2D, 3D elliptic genus. That's what it is in physics language. It is counting something. That's counting something means counting BPS states. Counting local BPS states in this combined 2D, 3D system, which is may look very complicated. Like QG. But this is actually also not too complicated. First of all, BPS states, this is fancy word that physicists invented for something that in mathematics we know and love. This is Gukov homology. It's the same type of Gukov homology that, for example, Pavel used in his lecture. So it's no different. Literally, and in fact, that's why I choose to denote it by Q. It's the same kind of Q. There's T-charge, supercharge. So these are very special states. So quantum field theory may have all kinds of junk, but somewhere there are interesting homology classes, and basically that's what this nice, whatever they are, BPS states. Secondly, in this context, I mentioned to you that this object as a function of Q is meant to be sum over something doubly graded, ij minus 1 to the I, to the j, and then dimensions of homology. And like homology. Previously, I wrote HBPS. I'm not gonna write that now. I will write Q instead for balance. So this depends on the manifold choice of P. So that was the previous formula, or at least one of the formulae that we saw on the board before. But now we have, we can just compare. For example, look at this. Since again, we started establishing that this is a theorem, and going forward, in fact, for you, this could be a good research project to basically turn this conjecture into a theorem. Again, establish it on more cases. But suppose this is true, and already in those cases where it's established that's true, we have one expression like this and another expression like this. Right? So there is an obvious conjecture that you can try to make by just comparing them. So in both cases, you express the same object as graded trace, but this graded trace is from different worlds. In this case, it's from some Gukov homology over a physical system, and you care about it if you want to construct homological invariants of three manifolds. In this way, it's from the world of quantum algebra. So natural thing, combining the two, so basically combining this with the previous one would be a conjecture, which is something that is only now being going to be checked. That is Hij_Q, or I'll write star star. B is nothing but that ZV, log VOA module. So that would be very cool if that's true. Again, I don't know if it's true. It's actually hard to check because you have to have really good control over many things here. But if it's true, that's pretty good because it means that usually we construct homology in low-dimensional topology via very long route, and you have to build complex, then take differential, and so on and so forth. That's basically what this Gukov homology is doing. But here, if this is true, if this conjecture is true, we can bypass all of that, just borrow the answer from this side, and that's it. So basically, we get the answer anyway. So that would be very cool. So this is maybe a very exciting, optimistic conjecture. So I think if we can call it a dream or some goal for the future, which is much harder than other problems I mentioned. It could be good motivation. In any case, this is trying to illustrate what this notion of spectrum or character or trace is just.
The question, so is there a central charge there, or is it zero?
Yeah, so that's okay. That's another question I wanted to come to next. Right, so when you have, Pavel was asking a very good question. In two-dimensional CFT or vertex algebras, there are so much data that when we communicate to a friend, that's a good idea to start somewhere. So there are many different VOAs and CFTs. The first thing we should communicate is some most basic characteristics. And usually they have a name. So they have, so for instance, one such basic characteristic is central charge. It's just one number. It's usually called C, or I'm going to talk about something which is called C effective. And it measures roughly a number of degrees of freedom in a system, but it doesn't have to be integer. So for example, for fermion, it's like 1/2. So meaning that fermion is Ising model is half of that. And then there is another set of basic numbers. So these are not characters. This is not like complicated functions. These are just numbers. In our value, I guess. And anyway, I'm going to skip. So, and then there is also a set of so-called conformal dimensions. And this is a set of numbers. I'll call them HI or I runs over some set of labels that depends on DOA or CFT. And this HR is nothing but ground state energy. So this is analogs of this 1/2. So in his question, Pavel asked me about the first one. I'll come back to it in a second. Let me talk about this ground state energy since I have that picture on the board. So for us, these are exactly these deltas. So that's actually a set of ground state energies. And some of you quite rightly before, when I guess it was lecture 2 or so, okay, this looks like an interesting quantum invariant, which is rather complicated. Why don't we simplify it? Why don't we focus our attention on just leading term? And now in terms of this spectrum of states, I can say that, yes, this is basically a question about ground energy of our spectrum. So that should be nice and easy. But interesting thing, we don't know what it is. So that's actually a good question. So correct this part. This looks very good direction. So homework or simple exercise is compute this deltas. In fact, for the family, I'm going to give it to you. There is only one choice of these, so there is only equals 0 case. We can just go delta of m for the following class of manifold. It's the simplest family. This breeze points here: sigma p1, p2, p3. So that's a useful exercise. More general problem which is not a homework, but a real problem. Identify or say what kind of free manifold invariant is this delta in general. I mean, you can compute it, but can we express it in terms of more basic invariants, something like, I don't know, Hassan invariant or something? Clearly, it should be expressed in terms of invariants, which are also labeled by spin C structures. And there aren't so many candidates. So if you're interested in the second problem, or if you have difficulties with the homework, talk to Joseph. So this is his cup of tea.
So it is a work in progress. So
Yes, it's work in progress. I hope it's okay.
maybe if I can comment, like, so we have a formal for the response queues, and it's.
But don't give it away for
Yeah,
it's a homework.
But for more general graphs, it seems like very complicated. It's just some special nice things which happens for like, simple graphs.
Yeah, so there is definitely more to be understood, and I think it will be very useful. And this is where these different perspectives start really talking to each other in a meaningful way. For instance, if you're more interested in vertex operator algebras or 2D CFTs, you can think about this question from the viewpoint of conformal dimensions or ground state analytic for these modules. If you're interested in free manifold invariants, you can go to your friend who is interested in CFT and find common ground. So that's why I think it's kind of exciting area, because we suddenly talk to each other, and on each side the question is non-trivial, it's meaningful, something for us to discuss. Luckily, there is a theorem. So we're not quite in a vacuum here, but there is a theorem which says that if you consider, so I'm gonna approach this title of integral lifts in this one. So this delta is integral lift of something. So it's an actual number, and it could be 1/2, 2/3, or it could be in between 1,000 and 1,001. So it's a fractional number, but it's not necessarily mod something. But if you take its mod reduction, namely consider this delta mod 1, mod integers, then it's actually equal to something else that appeared in low-dimensional topology, and is actually quite interesting. So it's not totally boring, it's slightly simpler, but this is so-called invariant of Higgs-Floer theory developed by Oswald and Zappo. Minus a half or plus a half, that doesn't matter because we're considering both mod 1. So these are also invariants of three manifolds labeled by spin C structures. So these are called correction terms. Correction terms in Higgs-Floer theory. And in some sense, this is the coolest thing that Higgs-Floer theory produced for us in the past 20 years, because it is these numerical invariants which were heavily used recently in identifying all kinds of cool facts about low-dimensional topologies, sliceness of knots, and other things. In particular, they were used to reprove Thom conjecture, that's about embedded surfaces in four manifolds, and Donaldson diagonalization theorem. So even though this is a three-dimensional object, because again, it has this homological origin, it actually can be used to prove these important theorems in low-dimensional topology. This is basically cutting edge, what we know how to prove. And its mod 1 reduction happens to be the same as mod 1 reduction of this delta. An easy check is that this, of course, is not true if you remove mod 1. It's not even true mod 2, so that was maybe optimistic, but in some case. But anyway, so here I give you a result, an easy exercise, and something to aim higher.
Really quickly, so you give us this sort of interpretation of the invariant as the energy structure of some system. Is that sort of a post facto analogy we're making, or is there something about the three manifold itself that produced the invariant that tells us what that system might be?
Not really. It's going back to physics origins of many of these things. So and just trying to literally translate what physicists would tell us.
So it's more like you just looked at the invariant and said, hey, this sort of looks like a spectrum.
Yeah, and then I mean, this invariants have physical interpretation, and then that physical interpretation it's literally energy. So it's
manifold itself doesn't tell us anything
exactly.
about.
Yeah. So that's in some sense this problem. So more recently, I'm, I guess, more of a mathematician, less talking to physicists, and I care about its intrinsic mathematical definition. And that's exactly what this question is. So yeah, they can interpret it as energy, but to me, this is actually useless. I want to relate it to well-defined mathematical invariants. Or if it's completely new, that's also interesting. If it cannot be expressed or anything we know, then one should give purely mathematical definition. And that should be, in some sense, easier, but surprisingly, it's not. It's the reason it's not is because it's analogous to many invariants which require like this ground state energy kind of or spectrum. It often requires some regularization. So in fact, this delta is analogous to eta invariants, if you know what I'm talking about. And those are also, even though they sound easy, they in practice they're actually not so kind of easy to work with. So anyway, right. So any other questions?
I have a question.
Yeah.
So, from the point of this, like BOAs or log BOAs, so the super trace, that means that these modules are Z2 graded, right?
Yes.
So like, are there also like naturally Z graded, or there are sometimes Z graded and sometimes just Z2 graded?
In fact, they're more naturally Z graded than Z2 graded. So maybe in that sense, super trace is not as good because there is integral grading I in that context. So I mentioned briefly this Felder complexes yesterday, and this Felder resolutions. So in all of these logarithmic theories, what one has is one should think about it in either derived setting or there is usually some analog of this homological grading, and that's the I. So in all of those setups, there is more natural C grading than Z2 grading.
Okay.
This mod one thing, how does one guess that there should be a mod one equivalence? Is it like, you had two real numbers and you ask?
Experiments. You just, you kind of start, I don't know, with some simple family. This is actually a huge family, but the answer is fairly simple. But yeah, so you experiment. And honestly, if you ask, like, do I know any other invariants of three manifolds labeled by spin C structures? I actually don't.
Okay.
So if you do, then
everything to the right of the decimal place was the same. So we're up to a shift by 0.5.
Well, they're rational numbers, so yeah, we don't have to worry about. I mean, they can be computed exactly in each case, and then quick comparison tells you, oh, they're really close to.
Just a comment. So that's kind of common in topology that some invariants are like equal modulo one, like it's really hard to construct this like integral lifts.
Yeah, so in my title, this is one notion of integral lift that comes up. And again, the statement here of this theorem is that reduction is easier and then the full control thanks to this theorem, but integral lift is something that surprisingly, as Joseph says, more interesting. But there is another integral lift and the second part of the title for this lecture that I'm going to transition to. So there are two integral lifts, not to be confused. This integral lift may or may not have something to do with another integral lift that I'm going to describe. Actually, that's a separate question if the two integral lifts are related. So, right, so somebody hands us this invariance of three manifolds which are Q series, and it's actually this being function of Q is a good thing because now one can try all kinds of limits. So what we just discussed is that near Q equals 0, so near origin here, this is Q equals 0, we have this connection to correction term. Here or that's exactly what basically this invariance delta that we need to understand further control, because they control the behavior near Q equals 0. So we already discussed previously that if you try to go near Q equals 1, especially if you do this expansion in H bar, then you should get connection to perturbative transients and again, hopefully to vectors of Constantine and other developments. And if we go to some roots of unity, we may get various invariants such as ABO, WRT, and so on and so forth, right? Something that's associated to quantum groups at roots of unity. So we have whole, like this is geography of this. But another question we can ask, somewhat related to this, in fact, is what happens, I mean, how fast these coefficients grow, okay? So what is their rate of growth? And here I'm gonna give you another homework. And then I'll come back to a question for our setup. Make a practice round and estimate or try to figure out how the coefficients, the Q expansion, Q Fourier coefficients of the following function grow. Let's assume that it's just f of Q given by Q squared to Q infinity for Heimer divided by Q infinity. Let me check if that's correct. So in first lecture, that's correct. I told you what Q-Heimer symbol is. You can immediately code it in any language you like, mathematics, Sage, Python, you name it. And it will give you 1,000 coefficients. Just make a plot and take a look. It's fun exercise. But more importantly, get an estimate. I mean, try to make mathematics out of it, not just the root. Sorry, that's the root. Huh?
How do the Q coefficients grow?
Yeah, grow, yes, sorry. That's how the Q coefficients of this grow, yes, sorry. Yeah, I didn't finish the English sentence. Thank you. So why is this relevant or interesting? Because it's a general fact. So here I was giving a picture of some spectrum of Q of T and whatnot. Suppose you have Q of TD. That means D is space-time dimensions defined on D-dimensional manifolds. So D equals 2 is relevant to cortex algebras. D equals 3 is relevant for us, but not defined mathematically. Then it's a general fact that these braided dimensions that I just erased, so at energy n, dimension of Hilbert space braided by this energy level n grows roughly as n to the d minus 1 over d. So in particular, if d is equal to 1, we're talking about quantum mechanics. Things don't grow, and that's consistent with the fact that the spectrum I was showing you is typical quantum mechanical spectrum. It doesn't have much growth. At every state, you have same number. So it's like, or rather, actually, I should say log of this. I apologize. It's exponential. So in particular, so we see that this is n to the 0 if d is equal to 1. It's actually n to the 1/2 if d is equal to 2. And it is a theorem. Actually, I don't know due to whom, probably some of the founding fathers of vertex algebras like Lipovsky and others, Frankel, Igor Frankel, maybe others. But in physics, it came from Cardy, John Cardy, and it's called Cardy formula. It says that this coefficients Cn grow exponentially. Indeed, as this general statement says, namely a square root of n. But then there is a coefficient in front, and that's exactly this central charge that Pavel was asking me about and that I promised to get them to. So it's a square root, 1/3, central charge, I'll call it C effective, times n under the square root. So it is a more precise version of this general scaling that you can actually get in any dimension.
This is true for logarithmic things as well.
I'm gonna get to that. So this is a theorem. Yeah, thank you. So in fact, one quite rightly points out to the fact that I should be more precise here. So this theorem is only a theorem for a nice class of vertex algebras that we understand really well, that go back again to founding fathers, Borchers, and others. So I should say for rational. So that's what nice means. For rational, I'll put it on code because I didn't define the term. VOAs and CFTs, whichever version you prefer, you have this. That's a true fact, mathematically true. Our question will be indeed to ask, does it hold here? I'll come back to this in a second. But first I want to point something else. So again, this is general formula. Cardy made a contribution by making the coefficients precise. He nailed down that it's not only exponential of square root of n, he said it's 2 pi, 1/3, and then this has independent meaning, and people love this number already. So that's exactly the central charge that Pavel was asking me about. So, right, if I continue with this formula a little bit further, so to d equals 3, because I told you that this originates from some 3D, 2D coupled system, blah, blah, blah. So in particular, it has 3-dimensional QFT in the game. That's why it's a little bit outside of normal mathematics. So this would be 2/3 for d equals 3. And it's true that states in this 2D, 3D coupled systems grow as fast as exponential of n to the 2/3. But it's interesting fact, which didn't have to be true, but it is true, that if I look at homology of this physical system, namely look at this BPS states, they actually still grow only as exponential of n to the 1/2, not 2/3. So all states grow much, much faster, but somewhere there is a smaller space of states, these nice ones, like Gukov homology classes, and then they grow very much like in a theory 1 dimension lower. So that's kind of the magical thing. So I'm gonna formalize this in a second. But that's what I wanted to explain. So in particular, if you this is some partition function of a 3-dimensional theory, very much like what we are working with. But if you actually do this homework, you'll find that its behavior is similar to the 2-dimensional case, namely it's exponential of n to the 1. So now, what's the statement, or what can we say? When I started learning the subject, I was expecting that we should probably see same, this is called Cardy growth, but we should see same Cardy growth even for logarithmic vertex algebras. That was sort of my naive initial expectation, because unless I'm told otherwise, I worry about generalization. Of course, one should worry that if you enlarge the class, now anything can happen, but very optimistic hope would be that nothing happens, it's still this formula. But I should have realized even from day one that it cannot basically have a chance to work for several reasons. So one reason is obvious, because in rational CFT, this number C effective, so that's another theorem, is actually non-negative. And it's 0 only if theory is completely empty, so I can just say that it's positive for anything meaningful. But we already know that in logarithmic theories, this is not true. So this has to do with unitarity and so on, and being logarithmic makes them famously non-unitary. So this is violated in logarithmic form. So therefore, this already requires some modification. And here is a precise statement, which is very recent. So the statement is that in our setups, including all the set has, but also actually more general context, so assuming so-called generalized volume conduction, I can explain what this is and how it comes in. In fact, I may even have time to sketch the proof. But you should take this phrase as some papers in number theory which start assuming generalized Riemann hypothesis. So this is a kind of statement that everybody believes is true. There is no question about it. It's just someone will figure out proof at one point. So and then again, it's not even controversial or interesting. Like smooth Poincare conjecture in dimension 4, we don't know which way it's going to go. I mean, this we do know which way it's going to go. So this is more like P versus. Anyway, what one can prove then with this assumption is that this coefficient Cn grow as real part. So first of all, we would have to have real part because coefficients are actually real, not complex, but taking square root of negative number, or in fact, more generally in this logarithmic CFT is the C effective can be complex number. So we have to make something real out of complex. So that has to be this part. But then several other things may happen. So it's exponential of similar thing to pi square root 1/3 C effective times n, except that now this number can be complex value. So that's one approach. And in addition, something that I didn't anticipate at first, it could be a term 2 pi times r times n, where this r is rational number. So in particular, if you do this homework that I just raised, you're gonna find the following. So if I make a plot of this Cn versus n, the usual Cardi behavior would tell you that the growth is exponential of square root of n. So it's not polynomial, it's not exponential, it's very specific. It's exponential square root of n. So here, what you would see instead, at least generically, is that because this is complex, what you'll find is that there are oscillations. So yes, there is in absolute value growth of exponential of square root of n, but there will be all kinds of oscillations controlled by imaginary part of this context. Moreover, what you'll find is that there will be several branches, so to say, of that's fine. So there will be several branches like green and red, and I'll try to draw another orange one. And the number of branches this picture will be equal to the denominator of this R, rational number R. So this second behavior is somewhat more surprising. And has not been observed. So first of all, both oscillations and this fractionation into several curves is not seeing unusual rational VOAs or CFTs. So there you have something nice and just one single curve, but already this exercise that I showed you will be a good illustration of how this phenomenon plays out.
So is there a different theory for every rational number R, or like,
No, it's R is determined. So both this number and this number are characteristics of CFT or VOA. So characteristics of CFT2 or vertex operator algebra. So they're determined by your choice of theory. For us, it's determined by choice of graph, for example, or more generally manifold or whatnot. So, in particular here, I'm assuming, so this was derived in the present setting relevant to this three manifold invariance, but natural conjecture is that this behavior now holds in any, so that this is true in any logarithmic vertex algebra. Again, I don't know counterexamples, and it would be nice to test and explore it. So that's something.
Is there some interpretation of R akin to central charge, you know?
Not really. I can try to sketch where it comes from. So the proof of this formula that I showed you. So this is going to be like sketch. For a more complete version, I can refer to, so this is joint work with May Jagadale from just last year. So like I say, this is fairly recent, 2023. So there you can find the solution to homework as well as sketch of the complete version of what I'm going to give you. And the way Cardi proves his formula is the following. So if you want to extract behavior of the coefficients, this Cn, so one of the things we can do is to write Cn as integral of dq over 2 pi iq q minus n, and then whatever function we have, for example, this z hat of q. So that's an obvious starting point. And then question is, what do we want to do with this contour? So we want to push the contour to, in the same q plane that I keep redrawn, close to the boundary of the unit disk. So close to here. And the way Cardi got his result is basically by asking what is the saddle point that dominates the expansion. So what happened for him is that it was basically q equals 1, which was always dominant. But here, what happens is that some value of q, which is q equals e to the 2 pi ir, that dominates the expansion. And of course, there is a similar point here because this are real one. So that's where this peaks, and that determines the R. So what you're asking is a very good question. It's first time I encountered this thing. Again, it's fairly recent, so I have no idea of what the interpretation of this number in terms of VOA, CFT. It doesn't look the same like central charge. It's not like it's counting number of degrees of freedom, but I don't know. It would be good to give more details. So it's some characteristic, new characteristic of CFT.
Sorry, I didn't quite understand what's the difference between theorem and conjecture.
So theorem is that in the setting of this Z hat invariance, that's a theorem. There was a conjecture that in some cases they're known to be characters, but conjecture is that they give characters of log VO. So if you compose this theorem with a modularity conjecture, then you get this one. You get prediction that in log VOAs, VOA people should expect this. But I cannot prove it using VOA language. I can only prove it using this quantum group invariance. and the conjecture that they happen to coincide. So this is an illustration of how this feeds into this data set.
So it's a conjecture about VOAs that you get from looking at the.
Exactly.
Yeah.
It's a conjecture about VOAs that we get by this interesting duality that this happen to be characters. Assuming. So that's probably one of the best things I can say about this R. I don't know if there is I think there are various details, but it's I can't really show my time. Okay, but I can say something about this C effective. It's a complex number. So again, we're discussing a very simple question. I give you a very simple definition that we can explain in undergrad, how to compute this in so many examples. So now what we're doing, basically we're experimenting. We're trying to figure out what the structure is. And it turns out to be surprisingly rich. So the point is that with very simple entry point, you get a connection to fairly advanced questions. So let me, as a last item, discuss what this C effect is. Again, R is some rational number, but you can compute it in each case. In fact, it would be good to, maybe I should pose a problem. Yeah, I was going to pose the same problem about C effective, but I can also ask so if this is manifold invariant, so natural problem based on questions that I was planning to ask and you're already asking is to ask what kind of what three manifold invariant is C effective, because it's determined by the manifold, at least in our setting, and also this rational number R of that. So I don't know, but I'll tell you a little bit about C effective. Very much like the previous statement about behavior near Q equals 0, namely the deltas, it's easier to say what's mod 1 reduction of that is.
Is this problem known in the rational case?
Oh,
Is this question known in the rational case where you don't have R? What kind of three manifold invariant?
well, there are very few choices of M that connect to a non-logarithmic VOAs. So in that case, actually, that's a good question. I don't know the answer off the top of my head. In fact, I don't know the whole class of such manifolds when this is not logarithmic. That's another good question. In this territory of three manifolds, which three manifolds relate to non-logarithmic, usual rational vertex algebra? I don't know the answer. It's some very, very small subset, but I don't know how to characterize it. So it's even there is a good question. Right, but you can have that following statement that very much like in the theorem about deltas, it was easier to say what the mod 1 reduction is. So here, rough statement is that C effective, something like mod 1, it's going to be in quotes, meta statement, mod 1 is equal to Simon's value of some complex flat connection, alpha. So this is SL2C. We are working with rank 2, so it's SL2C flat connection on our manifold M. Okay. So then question is which one? So I'll denote it by a star, because a generic three manifold, in fact, of the type that we're discussing may have easily hundreds flat connections and components of various dimensions. So for instance, even just as an example, if we take the simplest, most boring family of Brice-Korn spheres, so for M, which is sigma P1, P2, P3, the total number of flat connections is complex flat connections is P1 minus 1 times P2 minus 1 times P3 minus 1 divided by 4 plus 1. And you can see that if I pick P1, P2, P3 roughly on the order of, I don't know, a dozen, 11, 13, 24, then this is going to be like 100. So out of 100 flat connections, which one is this? Because this asymptotic growth of coefficients is dominated as precise number. So this plus 1 is a billion one. So it's special because it has large stabilizer. It's reducible, but it's not this one. So that would be more special candidate. And the other ones are all democratic. They're all completely the same. They're like children in a family, big Italian family, right? So how do you pick your favorite child? I have no idea. So it's actually a very interesting question from viewpoint of three-manifold topology or Chern-Simons theory. What on earth, out of this completely same democratic family of connections, yet theoretically there is no distinction. I can't see anything. I mean, this one has different stabilizer, but these ones are all the same. So out of this family, one is picked. So that's the guy alpha star. That's what I denote with a star. The obvious problem is how do you pick alpha star?
Do you know they're different mod 1 as you run around that bunch of children?
Different.
Since we're asking about things mod 1, I guess I was just wondering if I ran around the children and asked about their Chern-Simons invariant mod 1.
Oh, no, they're all different. Generically, there are sometimes coincidences, but that's very rare. Yeah. And even then, it's a natural question. Yeah. So that's obvious. Problem is not homework, because if you figure this out, write to me, or better yet, write a paper. I'm actually curious to know what the answer is.
Yeah, I think I have a guess, and that's because if you think of it as a singularity, then this corresponds to this spectrum, and that one is ordered by a Hodge theory.
Well, no. I want the answer for any three-manifold. So
Yeah.
if I give you hyperbolic surgery with coefficients minus 2/3 on figure 8 knot or 5/2 knot. So what's the answer?
No.
I don't know. So
Is there an average?
not that I know of. Again, it connects to the subject of resurgence, where you're summing over connections with various coefficients and so on. But probably what you suggest is in the right direction. I can't think immediately of an answer, because these are some transcendental numbers actually. So these are special values of dialogues and algebraic values and so on. So averaging or summing them not always is like nice operation. I don't know actually. So there is a lot going on. So it's also not true that there is no structure at all. They are controlled by block group and other things. So maybe they're, I think the answer may be yes. I just don't see, as Constantine says, forest for the trees.
Sorry, I missed where the statement came from. Is the statement that the CFF is in fact the Chern-Simons on some distinguished flat connection? Is that a theorem or a conjecture? Or?
That's a conjecture, but it's incorrect conjecture for several reasons I'm going to prove. So that's something that you would be led to, or that's observation in simple examples. That's probably the best way to say it. So only in simple examples, this is observation. It's expected that something like this is true in general, but I'll tell you two ways in which this is still very poor. And then I'm ready to stop. So first of all, the C effective, where is that? Okay, this is C. So look, these are actual numbers. This is something we can put on a computer, see the growth and so on and so forth. So this is a number. It can be, for example, 15.734, blah, 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 and so on and so forth, right? So it's not mod 1. So first of all, not only I have to choose, so this statement, the way it's written is cannot be right or useful for us, because I need to remove mod 1, because C effective is an actual number, I think. So I'll try to correct it now. So C effective is equal to this, but now I have to use notation that I briefly mentioned the other day. I have to actually specify the integral lift of alpha. So what this is, it's transaminds of this special connection in the usual form. This is mod 1 object, and let me put it in the range between 0 and 1, and then I'll have some integer m star. So to me, actually, more important problem is, or maybe equally important, so this is picking favorite child. Again, I have no idea how to do it. As a gauge theorist, I see no gauge theoretic way to do it. But another equally hard problem is identifying what kind of three manifold invariant is this integer. What is m star? I mean, we love three manifold invariants which are integers, and we can compute it. And because the whole thing is extremely computable and so on, you can even train neural net to start recognizing or find connection between this integer and some other integers that you feed into the set. But at this point, we don't even have a conjecture. So that's the integral lift in the second sense. That's analogous with deltas, where there is an integral lift, but we don't know what it is. So that's a very cool thing. And finally, the last thing, which is even more kind of interesting, is that in simple examples, this always happens to be normal SL2C flat connection on M. So this is true, what I just said, for some M, for some alpha star. But it is not inconceivable that if you go to complicated examples, we start seeing this non-flat connections. Remember, yesterday I mentioned briefly that this whole package embeds interpretive transassignments into something bigger. So we already see in resurgent analysis on a barrel plane singularities which are not only complex flat connections. If you go to surgeries on knots more than 10 crossings, you start seeing non-flat connections. So that's why I'm hesitating to make it a conjecture, because I suspect there may be non-trivial, but probably kind of example around, I don't know, surgery on a knot with 10 crossings, example where this is not even complex flat connection. It's one of these other things, settles from infinity, divisor infinity, at infinity that gets added to it. Anyway, so this is a lot to work on. I gave you homework, I gave you problems. Since I'm the last speaker, I have privilege to thank the organizers. So huge thanks go to Chris, Stefan, and Pavel. So thank you for bringing us here. Thanks for very exciting and productive.
Certainly would like to thank Sergei and all the other speakers for these lecture series that were very interesting. So thank you.
Sorry, any questions? So this C effective is coming from the growth of the series, as we pointed out, right? So if we also know that we can, by taking a limit approach like other known invariants, which would be then related to some conformal field theory, right? Like the Rosikin-Turaev theory, for example. So this would then relate.
No, so that's confusing things. So there are two relations to DOAs or CFTs. One is, and again, they live on two different sides of the 3D correspondence. So the one which has been studied for 40 years is the one where you take three manifold M3, chop it with some surface of, say, genus G, and find some CFT or VOA whose conformal blocks live on the surface. So that happens just in 3D side. So this other VOA lives on a side of 3D anecdotes 2 theory. That's where we have Gukov homology. This Gukov homology is basically related to this new VOA. Another hint or answer to your question is that this VOA depends on type of transassignments theory on M3, whereas VOA we're talking about depends on 3 manifold. So the old-fashioned WZW is not going to change if you go from 3 torus to 3 sphere to complicated plumbing, but this guy does. So this VOA depends on.
That's what I was trying to ask, kind of like maybe if you take the limit, it would tell you which WZW you have sort of an which central charge in that regard. I don't know if that's.
No, but that's unrelated to this guy. So this is completely different relation because there you would, so there, in this story, there are two DOAs or Kazdan-Lustig correspondences acting actually. One is direct relation between TQFT and DOA in an old-fashioned sense. So here we can ask, okay, and this can be a table, like we take that hat, it will correspond to some complicated VOA. Actually, it's hard to describe what this is, but this is huge thing. It's like, let me say monster, I think. It's pretty big. It's kind of like a monster view. So then you take Q2, in this TQFT, you take Q2 to unity, you find more traditional, I don't know, RT, other invariants, and this becomes more tame like WCW, okay? So that's one connection. But then there is another connection that in this world, because these are Q-valued invariants, you can actually ask, is it possible that my Q-valued invariant is character of something else? And this will change from manifold to manifold. So that's yet another connection. So I think this equals kind of Q for some other CFT or VOA. That's the new relation. And they're completely different. I have no idea how to connect them. I mean, one depends just on a TQFT, the other depends on a three manifold. And again, in the second one, we had no chance seeing until we actually work with generic Q, because the roots of unity, there is a statement cannot exist.
I was wondering if you could elaborate a little bit more on like the non-unitarity in mod CFTs.
Well, other than saying that they're non-unitary, I don't know. So logarithmic means several things, and there are like paradigms that are all related. So representation theory of logarithmic VOAs is non-semi-simple. That's, in other words, you have extensions like Jordan blocks, and this is already like monodromies of logarithms. So, if you try to do modular transformations of these characters, they are not going to be modular or vector modular in usual sense. They start involving tau, and because tau is log of q, that's another way why they gain the name logarithm. And the third is that correlation functions are not just controlled by conformal dimensions, nice powers, but they actually have logs. So, and for all these three reasons, logs have nasty property or beautiful property, depending how you look at it, that they have monodromies. So all this non-single valuedness is responsible for lack of unitarity. And as a result, so I guess starting with any of these three descriptions of logarithms, it's no surprise that when we try to compute central charge, we get, in general, not necessarily positive real number. We quickly get, even in simple examples, negative number. So beaten to that families of singlet, triplet, log VOAs, these are like canonical examples, have negative central charge. I think on a board I wrote at some point 1, P, either singlet or triplet, and it's a family labeled by P. So P is, for example, non-negative integer, but central charge would be something like 1 minus 13 minus 12 times P plus 1 over P, if I'm not mistaken. I think that's right. So for P equals 2, I want to get minus 1. Maybe it works, maybe it doesn't. I don't know, something like that. I got something of this. You can try to fix it or find it. And anyway, so it quickly gets in negative regime, and then also if we start digging further, it becomes complex number. But you're asking very good question. Like I don't think we have good understanding of many of these features, how to deal with that. That's why this log CFTs or VOAs are hot topic. And hot. Good questions.
Well, in that case, let's thank Sergei.
Also like to thank the audience for participation, very active participation, very many questions asked. We really appreciate that. So thanks very much.